All right, we're going to go back to regression lines a little bit. This is one reason we're going to review so much, because it's kind of reviewed a little bit like already. So remember that we had these regression models back in chapter 3 where we had like straight line relationships that describe stuff? So this describes the relationship between a quantitative response variable, which is the x variable, and one or more, I think I fixed this on your notes, it's supposed to say explanatory variables, right? I really wanted to go exploring instead of explaining, so, which are the y variables. Some books call x the independent variable, and some books call y the dependent variable. It's actually far more common than their whole response and explanatory, but whatever. Okay. I don't know what I'm supposed to put in the next blank. I didn't do it.
Dependent or independent, maybe?
The x variables are called predictors. The things you use to make predictions. Obviously, I'm not going to ask you about that word in your test. Okay? All right, so moving on. So what was the form of the regression line? We didn't say y equals, we said, remember, y hat equals. And I think the notation we used was b naught plus b1x. That b1 is your slope, and b naught is the y-intercept. Pretty much same as y equals mx plus b, right? Yeah, the response should be the y. I just dyslexified it in the start. Yep. Okay, so for a specific x, like suppose this equation talks about heights of women in a college class, okay? For a specific, oh, that's not terrible. Heights of women of a specific age. Here we go. You pick a specific age, y hat would find kind of like the average or estimated height at that age. Does that idea make sense? It's kind of like the middle value. So suppose we had something that was age, height. And for a while, it does kind of go line-ish, right? Eventually, it levels off and we stay the same height until we shrink. There we go. But we have an age, and then we have an average height, right? Is everyone going to be exactly on that line?
Yes.
That was sarcasm, right? Obviously not. Everybody that's the same age isn't the exact same height, right? Okay. So first of all, so y hat is the predicted or estimated mean of y. So it's the estimated value of sort of like the average height. This point would be the average height of all people of that age. This point would be the average height of people of that other age. So it's kind of like averages for every single value of x. B naught is the y-intercept of the line. So when you have a y-intercept, where your graph crosses the y-axis, what is the x value at that point? Zero. And I think we talked about this a lot, that occasionally had meaning and sometimes it doesn't, right? There was like it could have been the price of a car when it was first sold, or length of hand span when you're 0 feet tall, or something stupid like that. They don't always have meaning. B1 is the slope of the straight line. This tells us how much an increase or decrease for y hat happens when x increases by 1. So like if age goes up by 1, how much does height increase? Okay. And do you guys remember how to find residuals? This is the how much an individual observation deviates from the predicted value.
The actual minus predicted.
Observed minus predicted, or actual minus predicted. Or y minus y hat. Okay, so let's review an example, because this basically is last time. So suppose that medical researchers use sample data to find a regression line describing the relationship between systolic blood pressure and age for men between 40 and 60 years old. So what happens to blood pressure as you age on average? It goes up, okay? So this regression line is given by, you estimate the blood pressure by taking 85 plus 0.9 times age. Because the slope is positive, you can tell that as age is increasing, so is the blood pressure, right? So that's y hat equals 85 plus 0.9x, right? Your book likes to write these with the words, but I get lazy and write them with x's and y's. Okay, so give the value of the slope and then write a sentence that interprets it in this context. So what is the slope? 0.9.
So would you rather us do M or B1, or was it B1?
M or B1, no, it doesn't matter. Okay, I know what you mean. I just taught algebra for so long, I have a hard time using B1.
Okay.
But if you're going to use that notation, B1 is just fine. Okay. And then write a sentence that interprets. So remember that slope is change in y over change in x. What's y measuring? Increase in
Total,
it's a blood pressure, which I think we discussed was like millimeters of mercury. You don't have to know that label, okay? Like I would give you more information if I posed the quiz question. And then what's x measuring? So which is measured in years. And that's how I interpret the slope. I think, okay, what are its units? We have milligrams of mercury per year, right? So how much does your blood pressure go up if your age goes up by a year?
0.9.
So for every 1 year increase in age, BP goes up 0.9. And is this true? Is that what it is? Is it MMHG? Okay. I think so, but it goes up 0.9, whatever units this actually is. Is that true for every single person? No. So the way you say that is you just have to add the words on average. Because some people pointed out correctly that for some people their blood pressure goes down if they make like a health change, right? But on average the trend is up. And that's how you say it. It's the average change that happens. Okay. So estimate the mean systolic blood pressure of men who are 50 years old. How would you do that? Y hat equals 85 plus 0.9 times 50. So y hat is equal to, I think that's 130. So this is the average systolic BP of men who are 50. Does that idea make sense? If we found the average for men who are 40, it would be a different number, right? Or men who are 30. Well, you probably can't use 35 because 35 is not within your range from 40 to 60, right? Okay. But the point is it's an average for a specific age. Okay, suppose that the systolic blood pressure of a 50-year-old man is 125. What is the value of the residual for this guy? So is he below or above average? Below. So we want that to come out negative to signify the below. That's why we do y minus y hat. Because then if y is lower, it comes out negative. If y is higher, it comes out positive. So 125 minus 130 is negative 5. So this person's systolic BP is 5 milligrams of mercury lower than the average 50-year-old. Oh, I guess that was the next question, wasn't it? Okay, but does the -5 make sense? Okay. So, the next question just said, explain in words what the residual you found in part C indicates about the relationship, what we just said. So this person has a systolic BP that is 5 millimeters of mercury below the average for all 50-year-old men. Okay. All right. So much like the stuff we did in the last chapter where we had confidence intervals where 68% of the population falls within 1 standard deviation, 95% are 2 standard deviations away, and 99.7 are 3 standard deviations away. We could talk about all 50-year-olds. We could talk about how do all 50-year-olds vary about this line. Does that idea make sense? Like, we know what the average BP is for a 50-year-old, but then how much are those 50-year-olds going to vary around that line? So you can kind of think of taking your line and slicing it, and you'll have a range of people that's kind of bell-shaped and average-ish, normal-ish. And so we're going to go into hypothesis tests for these regression lines. And much like hypothesis tests use Greek letters for the means, we're also going to use Greek letters for the true regression line. So instead of using B's, the corresponding Greek letter is beta. So this thing called E, the expected value of Y is B naught, beta naught plus beta 1x. So that E of Y represents the mean or expected value for Y for all individuals. And note that Y hat is an estimate of this expected value of Y thing. So beta naught is the true intercept of the true regression line. What estimates that? I think you have your regression line, which is an estimate, right? Your estimate is B1 plus, or B naught plus B1x, so which one estimates beta naught?
B naught?
B naught. Beta naught is also the y-intercept, right? So the true y-intercept is estimated by your regression line y-intercept. And then what estimates the slope? B1. Okay. So heights and answers to the question, how much would you like to weigh, were recorded for 126 women in a statistics class. A regression equation for y equals the desired weight and x is the height was given by this. What is the value of the slope? And then write a sentence that explains what this value shows about the relationship. So first of all, what is the slope? And let's use the B notation. Is it B1 or is it beta? It'd be B1. Why is it almost never going to be beta? Beta is the true value, which means you would need everybody. Does that make sense? So if I said it's my population is my statistics class and I ask my whole statistics class, then that's okay, then it's beta, right? But if it was like using the statistics class to generalize about all women, different story, right? Okay. What are its units? What's Y measuring?
Pounds.
Pounds, and that's your desired weight, right?
Yeah.
Divided by
Inches.
And I think on average, people who are taller understand that they have to weigh more than people who are shorter, right? That's kind of what this is getting at. Does that make sense? If height increases by 1 inch, how much people think their weight should go up?
2.9.
2.9 pounds on average, right? That's what they think. So for every 1 inch increase in height desired weight increases 2.9 pounds. And I should say on average, because that isn't like always true for everybody.
We wouldn't have to put that if we had the actual numbers. Or if we had the true value. Right?
It's still an average increase because it isn't as if every single person says that when my height goes up by height goes up by 1, my weight should increase by this much.
That's true.
Does that make sense?
Unless they were actually gonna.
Unless it was like everybody in your population. Yeah. Okay. So assume these women represent all college women. Like as in people that were surveyed are doesn't all it means they represent, which means that they're a representative sample and there's no biases, like I didn't only ask the basketball team. Okay? What is the proper notation for the slope? So I said that they represent. I didn't say that they were all college women. Does that make sense?
So it'd still be B1.
So it'd still be B1. The slope is found using sample data. Being representative just means that you can make generalizations from this line. So a non-representative example that came up really recently. So after the election, people are like, why did the predictors all get it wrong? And now that the election's over, stuff is starting to come out. And have you guys ever heard of a website called 538? I should tell you about this. You should look at it because it's all sorts of cool statistics. It comes from the 538 people who are in Congress and in the House. That's where the numbers come. But this guy is a really good statistician, and he runs all sorts of data and does all sorts of data about the election in particular, including basketball and sports and other crazy stuff. So you could go there and read some fun articles. He thinks that the problem with the elections polls were that they underrepresented certain groups, and it wasn't a representative sample. In particular, he says that they didn't ask enough uneducated white voters. That's what his preliminary analysis says. So, just FYI, if you care about it, I'll email out the link just because it's an interesting thing to read about, not because I care one way or the other, because it's all over and done, but it's an interesting statistical thing for this class because it's something that happened that was not what the statistics said it should be, that you actually experienced, which is kind of cool, right? Well, I mean, you know. Unlike just like a Truman election that happened, like, 50 years ago, people should have known better now, basically, is my opinion on that. Okay, so what is the estimated mean desired weight for college women who are 65 inches tall? How'd you figure that out?
What is X with 65?
Plug in X to 65. For those of us that can't translate that into feet and inches, how tall is that?
5'5".
5'5", yep. I can actually do that one, but. Okay. And I got that people who are 5'5" on average want to weigh 123.1 pounds. Man, that's skinny.
It's just the height, it's just the height.
I'm 5'7", and I'm never going to weigh anything near that or 10 pounds over that ever again. Okay. So does that ring a bell for regression lines from last time? That stuff will be on your final, so like guaranteed. To like interpret the, make a prediction, interpret the slope, find the residual stuff. It will be there, I promise. Okay, so make a note to yourself it was on test 1. Yes?
So with the represent, if it says represent, it's going to be B1, and if it actually is, it's going to be
If it said something to the effect of the data are all people in the population, then it would be the betas.
Okay.
But if it just is it's a representative sample, it doesn't mean that it's still B1 because it's still data.
So like a census.
A census, if you brought the equation from the census, then you could certainly say that it was a beta.
Okay.
Yep. Although really even censuses don't catch everybody,
Yeah.
right? So usually the beta is like unachievable because it just would involve looking at everybody. Unless you have a population that you can kind of confine to, like say, oh yeah, we're gonna look at all of UAF. Where you could theoretically ask everybody at UAF. It's not that hard. Okay, so we're now going to talk about how much variance, how much spread there is among that regression line. So some things we assume, just to make the generalizations we're going to make, we're going to assume that there is constant variance. So think back to that blood pressure example. We had a predicted blood pressure for a guy who was 50, right? We could have also had a predicted blood pressure for a guy who was 55. Does that make sense? And we're going to assume that how 50-year-olds vary is the same as how 55-year-olds vary. That the spread is the same. Does that make sense? And the spread is the same for 45-year-olds, okay? So it's kind of like around your regression line, people are spread out the same amount. So the general size of the standard deviation of the y values about the line, oh my gosh, line, spell check doesn't catch that one, is about the same for all of the x's. So given a specific x, how much spread there is the same as for another x. And then we also assume that for each specific value of x, the distribution of the y values is normal. And if we assume that that's normal, that means more people are in the middle, right? So you have 68% plus or minus 1 standard deviation, right? And then you have 95% are plus or minus 2 standard deviations. And how many are plus or minus 3? 99.7. So if you have, say, the average blood pressure for 50-year-olds and you know the standard deviation around for 50-year-olds, you could figure out what proportion of 50-year-olds are within like a range of their blood pressures. That's sort of like normal. Okay. So for a regression model, the standard deviation measures roughly the average distance of y values from the mean or from that regression line. And finding the standard deviation, here is its big, long formula, and I made a little bit of a typo, which I maybe fixed in your notes. This should be squared. Did I fix that in your notes? I did? Okay, good. So what you do is you find the residuals, which means you take every single y point minus the y hat point, square it, add them up, divide by n minus 2, take the square root. This is often going to be given to you. You're not going to have to find this yourself because it's too tedious. Okay, I'll just tell you that this is the standard deviation, but that's where the formula comes from, okay? It tells you how spread around the line data points are. Okay. Now, previously in chapter 3, we learned the squared correlation. Remember this R squared thing? Well, the R, what numbers did R have to be in between? Do you remember that?
0.
R was between -1 and 1.
Oh.
Remember that? That's the correlation coefficient. Positive means, as x goes up, y goes up. Negative means as x goes down, y goes down. And actually, equal to is okay, right? I should have specified that because that means your points fall in a perfect line with positive slope, right? Or perfect negative slope. But when you square stuff, what's R squared between?
0 and 1.
Okay. That statistic is also denoted by capital R squared, and the common phrase to express this is the proportion of variation explained by x. That's kind of the proportion of variation of y explained by x. So how much of that variability can you predict just knowing what x is? Like how much variability in your grades can I predict knowing what your homework grades are?
Yeah, is that the thing I was confused about? The capital R and the lowercase r are different things.
Not really.
Oh, okay.
No, they're not. It's just the notation is commonly actually capital R squared.
Okay.
That's much more common. So if you use capital R squared or lower R squared, I'm not going to be picky about that at all, okay? So use either one. And here is a formula that you use to find that. And statisticians love abbreviations. We take other classes, you have to use these sometimes, so just keep in mind what they are. SSTO, that stands for sum of squares total. And the official formula for that is this. You take all the points, and you take away the mean, and you square it. So what this measures, if you take yi minus your average, that's how far away are your data points from your average. That's how much do your y's vary from the average. Does that make sense? And the reason you square it is because then you erase the negativity of stuff. Okay? I don't know why I skipped SSE, but let's add it. SSE is equal to sum of squares error, which was on the previous page, but it's worth reviewing. That's how much your predictions were off by, like what your errors are for individual values. So you take your values you used minus your yi hats, and you square them. And you can prove that this equals something called SSR, which is the sum of squared regressions. I'm just going to use the fact that this is true instead, okay? Because I want to talk about why that's a good measurement of how close you are. So you guys know if R squared is close to 1, you almost have a perfect line, right? Does it make sense that when SSE is small, as in close to 0, R squared is going to be close to 1? Do you buy that? Yeah, and then the other thing is that this number is always smaller than that number. So this expression is always positive. So that's how you get the sort of measurement of how close you are. You'll have to maybe use that formula, but what I would do maybe is give you what these things are in output, which we'll do an example of that later, and then ask you to interpret it. I'm not going to actually make you do this whole summation thing. That part's too gross, okay? So we'll talk about how to look at that in like a little output thing, which I think is given next. Okay? So let's just do an example. So the temperature data set on this companion website gives us the mean April temperature in Fahrenheit based on geographical latitude. We live like really far north. As latitude goes up, temperature goes down, right? Also, elevation matters, right? So for some places at various latitudes, they are colder or warmer than they would be on average because of other anomalies, like Colorado's probably colder than average because it's at high elevation, right? Europe, like Sweden's at the same latitude as us, are they as cold as us? Do you even know why they're not as cold as us?
Sweden's awesome.
Because Sweden's awesome? No, it's the Gulf Stream. The Gulf Stream brings warm water up, and that warm water moderates their temperature. I have a friend who that was her project when she was getting her PhD, was the Gulf Stream, which she studied. Okay, so in that case, the slope being negative makes sense because as latitude increases, temperature decreases, right? Okay, so in the output given below, what value is given for the standard deviation from the regression line? So I know this picture is not very awesome. But you see at the bottom, there's this and then there's this, right? So the standard deviation is that 2.837. So for a given latitude, as in an x value, because our x value are latitudes, this tells how the temperature varies at that latitude. And because we assumed that stuff is normal, you know that it would say 68% or plus or minus 1 standard deviation. 95% or plus or minus 2 standard deviations, right? That's kind of what this is saying. Okay, and the R squared is given as 97.1. Write a sentence that interprets this, and that's just the second thing I circled. So R squared equals 97.1. So this is the proportion of variation in Y explained by X. So just fill in what Y and X are. Yeah.
Is it not 91.7?
Oh, it's 91.7, sorry.
Oh,
I so sorry. So the proportion, or of variation of Y explained by X, and I'd like you to actually fill in what Y and X are, but
So would that be variation of temperature explained by latitude?
yep, so 91, and fill in the proportion as well, if that makes sense. 91.7% of temperature variation. I don't know why I just spelled that wrong. Temperature variability is explained by what? By latitude. Oh. And if you take a more advanced class in regression, where you can find these lines with more than one predictors. So like last year in the spring, I took my calculus class and I used like their homework grade and their quiz grade and to try to predict their test grade. I had 2 different things I was using. Which one do you think was a better predictor of test grade, homework grade or quiz grade? Quiz grade was a better predictor of test, which makes sense because it's more like a test, right? Yeah.
You're simulating the
So-
stress too.
And simulating the stress, you simulate all of the conditions, yep, definitely. And so the way I could tell that the quiz was better was that it had a higher R squared value. It explained more of the variation in test scores. Okay. So example 14.5 gave this regression equation for that maximum sign distance at which a driver can read a highway sign and driver age. So what is the predicted value of the maximum sign reading distance for a driver who's 21? How would you find that?
Plus 21 over X.
Exactly. So I got, this was about 513.79 feet, which I'm just going to be, for simplicity, I'm going to say 514 feet. So the average 21-year-old can read a sign when they are 514 feet away from it. Some people are more blind than others, but this is the average 21-year-old. Okay?
Definitely one of the more blinders.
Yeah, I don't know. They must do this without glasses. I don't know.
Yeah.
So compute the residual for a 21-year-old driver who can read the sign at a distance of 525 feet. So the residual is y minus y hat. Is this person above or below average? Above. Yep, so it should be a positive answer, right? So 525 minus 514 is 11. So he can see 11 feet farther than the average 21-year-old. And a reasonable question to ask is, like, how much do all 21-year-olds vary? Does that idea make sense? Like, what's the sign distance at which most of them can read something? We've also put signs at like that lower threshold, you know, before exits and stuff on roads where exits matter, not in places like Alaska. Okay.
I'll just take the next one.
Except for in Anchorage, where they matter a little bit. A little bit. Nothing like Minneapolis. So the standard deviation of the regression line in this example is about 50 feet. So I just told you what it was. Okay? Now just use the empirical rule. Give me an interval that describes the maximum sign reading distance for about 95% of 21-year-olds. So what do you use for your average 21-year-old?
514. Yeah.
It's 514. So your 95% of them are 514 plus or minus how many standard deviations? 2. This is how I'll test the empirical rule on your final. Does that make sense? Instead of asking a question like the one that was given on your first test, it'll be embedded in a question like this. So that's what, 414? 2, 614, yep. So then you might say, okay, well, I'll put those signs at 400 feet because that means most people can see them, right?
Most 21-year-olds.
Most 21-year-olds, yeah. That's true. We probably shouldn't base our predictions on them. We base them on like the 75-year-olds.
Yeah, but I think they do that because that 21 is,
Okay, so 95% of all 21-year-olds.
Do not have question D.
Question D doesn't ask that.
Okay.
Have a max sign reading distance of between 414 and 614 feet. This part D is this 21-year-old special?
yes.
Yes. So is it unusual for them to read the sign from 650 feet? Yes.
Because it's close to 3
And then 3 standard.
It's close to 3 standard deviations away. Really, it's in the top 2.5%. Does that make sense? Yeah. This
On the other end of the 95.
exactly. It's on the other end of 95% confidence interval, so they're in the top 2.5%, and that kind of makes you special, I think, right? This person is in the top 2.5%. And if that's all you say, or if you said that, they're almost 3 standard deviations from them, that's also totally fine because it is pretty close to 3 standard deviations away, right? Totally would buy both of those. Okay. If you take a statistics class after this, you might see tables like this that get spit out by when you make a computer find you a regression line, because finding regression lines in practice is really tedious and you make computers do it for you, almost universally, okay? So I want to just point out what SSTO is in tables like this. So if you have to find them in the future, you can, okay? So it'll probably be a homework question, but probably not a test question. But if it is, I'll definitely tell you. So SSTO is sum of squares total. Tells you the total variation or total variance. So do you see how I have this column that describes variance? Which one do you think is the sum of squares total?
SS.
The bottom one.
The one at the bottom. Does that make sense? You got SS. SS is sum squares total. So SSTO is 1746.8.
Why is it STTO instead of SSTO?
That's really interesting because the book that statistics books do not have consistent notation. Okay, it's
Yay.
really, and it's also true at the graduate level, it's supremely annoying, okay? It's because it's a newer version of mathematics and they didn't standardize. SST is another common thing for this. So it just happens. SSTO, your book uses, the book I used for a more advanced regression class last semester used SST. Sum squares total. They're pretty consistent on SSE though. Most of them use that. Okay, so the next one we have is SSE. So we still have this sum squares error. So we had total, which one do you think is this was from the residuals, right? So which one do you think it is? 144.9. Because that was sum of square errors, it came from the residuals. So sum of square errors. Okay. And remember that SSR was equal to SSTO minus SSE? That was on that last page we had. So SSTO, this was the 1746.8 minus 144.9. 1601.9, and look, that's this guy. Sum squares regression, which if you know that's what that is, go ahead and just say it. And then part D, I just want you to be able to calculate R squared from the values. The values are just tell me what R squared is. So this was SSTO minus SSE over SSTO, right? That was the formula for this. So I think that top is 1601.9, right? What's the bottom? Great. And punch that in your calculator real quick, and you should get, no. It is less than 1, do you buy that?
Yes.
Because numerator is smaller than denominator, yeah?
Denominator?
Sorry, it's hard to speak to people and like multitask and, public
It's
speaking.
like a name.
Okay, 0.917. This is the one from that April cities thing we said, same as before. Okay. Is that all right? Okay. All right. So the last thing we'll talk about is a little bit of doing hypothesis testing with regression lines, and then we'll be done with this. So the statistical significance of a linear relation is testing whether the population slope is 0. Remember that 0 means that there is no relationship between the variables. Because if your slope is 0, changing x doesn't change y. So the things that you're testing here are, is the population slope 0? And testing that tests whether or not y and x are related. Like suppose I wanted to test, is attendance related to grades, right? And I'd be testing, is the slope 0 or not? So slope being 0, no relationship. Slope being non-zero means that there is a relationship. Okay. And this sample statistic is a t statistic. And you find that using this formula, you use B1, which was the estimated slope that you found, minus 0. Why do I use 0? Because that's the null value of no change, yep. Divided by the standard error of B1. And this thing is the formula for standard error of B1. And then there's n minus 2 degrees of freedom. We don't really do like super much of this at all. We're just going to look at the tests and interpret them. Because to actually find the standard error, you'd have to do that big old sum thing, which would be tedious. Does that make sense? Okay. So suppose I just gave you a data set. Do you guys have an example? Is this your next? This is not your next one, is it?
Our next one's
That's
a
a
table.
It's a table.
Yeah, linear regression.
GPA, this one, right?
Yeah.
Yes, okay, I had to cut some examples off of this, so here's the one. So the output for linear regression relating GPA and hours spent using the computer. The data are from this UC Davis. So 11 of the 173 students didn't provide complete data. Okay, so here is that regression equation. So based on your regression equation, are you suspecting that the slope is 0? As in that there's no relationship? Possibly, but it's never clear like how small is close enough to 0 for it to actually matter. For certain situations where your unit of measurement is really small, that can be close to 0 but still be significant. Does that idea make sense? Okay. So is there a statistically significant relationship between the two variables? Justify your answer using information in the output, and be specific about the null analytic hypothesis that you're testing. So your null hypothesis is that your slope is 0, which means beta 1 equals 0. And And because this is always a statement about the true values, use the Greek letter. And then what's HA?
Beta 1 is 9.
So no relationship. There is a relationship. Okay. So now look at this table. You have a row that says constant and a row that says computer. Coefficient, SE coefficient, T, and P. So which thing do you think you use to find the P value that's associated with the slope testing this hypothesis?
P on the computer.
Yeah, P on the computer one, because the constant is testing like how good is that number. Does that make sense? So the first row tests how good is your y-intercept. The second row tests how good is your slope. Okay, so the P value is 0.165. And is that less than our,
Is this
part
B?
Basically, yes.
Okay.
But this also says that basically the point is A and B are asking the same thing. Because it also said, is there a statistically significant relationship?
Okay.
So since P is 0.065, which is not less than our usual threshold of 0.05, right? We fail to reject H naught, right? Does this mean there is no relationship? No, because that would be accepting HA, right? So there is insufficient evidence to conclude computer use and GPA are related. And it's a little bit of a cop-out, but that's the statement you have to make. You can't say, oh, there is no relationship, because you didn't actually prove it. You just couldn't show that there wasn't one. So for now, you operate under the assumption that this is true, thinking that, well, maybe it could be disproven later. Okay? And suppose that rho denotes the correlation between the two variables, and this is testing whether or not there is no correlation or there is a correlation. That's the same as testing if there is a relationship. So it's the exact same test as part A. So this is the same as part A. The P would have been 0.165. And the kicker there is that testing the slope equal 0 is the same as correlation. But how that's probably going to come up is I'll give you a table and we'll have data and you interpret it, because that's how it comes up in later classes as well. They don't actually make you compute these things on your own. Yeah?
What is that row?
Oh, so rho is the true value of little r. It's a really good question. So little r is the number we use for correlation, which was an estimate from the data. Does that make sense? And rho is the true value. Does that help? Okay, does it make sense? Okay, remember that we have
Kinda like
B1 and we have beta 1, right? We have X bar and we have mu, right? We have R and we have rho. Okay, does that help?
Yes.
Yes. And it's like in the SAT, B1 is to beta 1 as R is to rho. She's like, oh, no. Okay. All right. More thing I care about a little bit more is how you find confidence intervals for the slopes. So this is much the same as other confidence intervals. So you take your slope times a t star times the standard error of your estimated slope. And the kicker here is that the T star is found using n minus 2 degrees of freedom instead of n minus 1. It's because of the two variables, the x and the y. That's kind of where that comes from. Okay. So I'm going to skip this one and do 8 first because 8 is more involved. And if I don't get to 7, you can look at it online because the notes should be there. If they're not, I'll add them later. No, I have them copied. So the slope of the line is 7. Is the proper notation for this slope B1 or beta 1? B1 is 7 because this is from data. So it's not the true value.
Beta 1 is the true value?
Beta 1 is the true value, exactly. The standard error for the slope was given in the output as, and this is a little bit wrong, I think I fixed in your notes, I think I said it was standard error beta 1, 1.581, yep. Okay, find an approximate 95% confidence interval. So the confidence interval's form is B1 plus or minus your T star times standard error of B1. And the degrees of freedom is n minus 2. So in this case, what's our degrees of freedom? 41. And if you look at your T table, T is approximately 2. So inputting those values, we have 7 plus or minus 2 times 1.581, or 7 plus or minus 3.162, or 3.84 to 10.16. So what this does is it gives us a range of values that could represent our possible slopes. Does that idea make sense? What were the units of the slope in this example anyway? Because it probably is also good to talk about.
Inches in height.
Yeah, so weight would be pounds, right? Height would be inch, right? So it's how much weight gain you have for every inch taller you get. Is somewhere between those values. Okay? So for every 1 inch increase in height, weight increases by how much?
Between 2.4.
Mm-hmm.
I have to say with 95% confidence.
With 95% confidence, yep. I should have put that at the beginning, but okay, last one. It has been stated that for every 1 inch increase in height, average weight increases by 5 pounds. Does the interval found in Part B explain this statement, or does it support it?
Yes.
Yes. As 5 is included in the interval, it is a plausible value of the slope.